streaming and start the browser.
Is it possible to ask a quick question from the one of the problems we went over in the last class?
Sure.
It was just it was, what's it called, the season, was it spring 16 exam 2, and you're going over the coin toss and you're asking like which one's loaded. I was reviewing the video for it and I just got confused at the very end for the last part of your answer. If it was leaning more towards the heads or tails, and how do you determine that?
Okay. All right. So we'll go to the exams first.
Okay. Okay.
Okay, so Bryce, do you remember which exam it was?
Yes, it was spring 16 exam 2.
Okay.
Yeah, because I wrote down, it was question 3 that we were going over.
Okay.
So I looked at what you had written and then reviewed the video, that section of the video, and most of it made sense. It was just the last question. I think it was the second.
Second question?
Yeah, it was like part C, I think, where it says, assuming the observations in the case. One of the parts I asked about, like, which side is it more weighted towards, heads or tails, if it is weighted, I think.
Okay.
Was that one?
All right, so let's go back to this particular question. This is what we talked about on last Wednesday. But there's a question about part C. Assuming the observation is representative of the nature of the coin. But this is important as an assumption because it is always possible that what I'm observing turns out to be kind of like all odd chances. They're not unlikely occurrences. So assuming that I'm observing the coin, and this is the way it's supposed to behave, present equations that can be used to solve the actual probabilities of a head, or a probability of landing on a head versus a tail outcome after a single toss. There's no need to resolve the actual values, but the equation should supply sufficient information to solve for the values. Use x as the probability of landing on a head, which means 1 minus x will be the probability of landing on a tail. And this part may use or reuse the parts of the other two parts. So that's basically what this question is asking. So now we are, so the answer is this one here. This is the equation that you need in order to solve for P. Okay?
Oh.
Yeah, because we know the left-hand side. Okay, so let me scroll up a little bit. Pretty sure people in the back, can everybody in the back see the entire screen? I mean, at least the browser. Okay. Okay, so this is resolvable because we know this is just a number, right? Okay, you don't need to actually give me the number, but we know this is a known value, which is what we need. And this is a known number. This is basically 4. This is a known number as well, right? So now we are looking at some number times p to the power of 1, which is just p, divided by times 1 minus p to the power of 3, divided by some other constant times p squared times 1 minus p squared. So now you have one single equation, but there's also just one unknown, so it is resolvable. That by itself is already sufficient. Okay, so if I were to write this out, actually as an equation, because I know it's a little bit hard to read like this. So if I were to actually turn this into equation, turning on the.
Are we recording?
I believe so. Okay, just hold on a second. Let's do this first. And yes, so we are recording, and the audio is up, so we're good.
Okay.
Okay. Put something here so we can focus on that. The camera itself is tilted a little bit. There we go. Okay, so I'm going to switch back to the other screen because I'm going to copy it. Because I just want to present what the equation looks like. So 79 divided by 146 is just a known number. And we're looking at the ratio on the other side. that only has p as an unknown. So just give me a second here to copy the equations. I'm done. So switching back. This is the equation. Okay, green is not a very good color. I guess it's sharper now, so it's a little bit better. So basically, this is what I'm looking for part C. Is that making any sense? Because we know that we have 79 observations of one head and three tails. We know that we have 146 observations of two head and two tails. Is that okay? So the ratio between these two observations should reflect the ratio of their probabilities. In other words, if I multiply this entire thing by the total number of observations, that should be about 79. If I multiply this entire thing to the total number of observations, that should be about 146. Yep?
The top part of the equation is your chances of getting one hit.
Yeah.
Out of all 4 coins, and then the bottom is chance of getting 2.
Yep. Yep. So this one, so you're correct. So the top part here is one head, three tails, and this one would be two head, two tails, which is what the question is providing as observations already recorded. All right. Yeah, go ahead.
I don't understand the 1 minus p. Is that just like the chances that you have left when you flip the coin?
Correct, because p is the chances of landing on the head, so the chance of landing on the tail is 1 minus p.
Okay.
Yep, go ahead.
So we're trying to find p ratio 1 minus p, right?
No, we are trying to find p. We're trying to resolve p. But this gives you enough information to resolve p already. Because, if you want to carry out the actual, thing, so you basically say 79, okay, blue, there we go. So we can say 79 times, this is 4 choose 2 is 24 divided by 4, which is 6, okay? P squared 1 minus p, the whole thing squared, equals to 146 times 4, because 4 choose 1 is just 4, and then we have p, and then we have 1 minus p to the power of 3. Is that okay so far? So what you do, there are easy ways to do this. You divide both sides by p, so then you get 1p left here, the other one is cancelled out. You divide both sides by 1 minus p squared, this entire thing goes away, this becomes just 1. Is that okay? So now you have 79 times 6 times p equaling to 146 times 4 times 1 minus p. I think that's pretty clear that it is solvable. Is that okay? Is that helping? Okay. But the question does not even ask you to solve for the actual p. You just have to come to the equation where the equation can be solved, and when it is solved, p is no. Okay, so which means if you can get to just this part here, the part that I'm going to circle in red, this is good enough. Now, obviously, if you can resolve it all the way down here, or even get down to the actual value of p, but I won't give you extra credit for actually resolving it. I just need to have the equation where it can be solved, it can be used to solve for the value of p. So that's what part C is about. So is that okay? All right. Are there any other questions about this particular one? Just to refresh your memory, the question itself tells you that we have 79 observations of coin tosses of experiments involving 4 coin tosses for each experiment. So there are 4 trials per experiment. Each trial is tossing a coin. So the observation is we don't know the total number of observations. We just counted and go like, okay, there are 79 observations of 1 head, 3 tails, and there are 146 observations of 2 head, 2 tails. And we need to work with just 2 numbers for this particular question. So once you solve for this p, if p is greater than 0.5, then there are more probability of landing on the head. If p is less than 0.5, then there are less chances of landing on the head. The coin is not fair. Is that okay? Okay, all right, cool. Shall we move on to another question? Okay. So, yeah, go ahead.
Is the cubed and the squared come from 4 minus 1 and 4 minus 2? Or
Can you repeat that question, please?
where does the cube come from for the 1 minus p cubed?
Cubed? You mean this one here?
The 1 minus p cubed.
It comes from the binomial theorem. So to really understand this question, or to know what information you need to answer this question, it is the binomial theorem. All right. So I'll switch back to the browser because we can move on to another question. So question number 1, I think that's where we left off. Let me see this is the one that I want to talk about. So question number 1 is about the same kind of question for all 3 exams. Did we go over this one already, or is this not the one that we went over?
I think we talked about it.
We talked about it? Okay.
We didn't go over it though.
We did not go over. Okay. So we can start with this one, and then we can move on to the other ones. So question number 1 is not necessarily a combination or binomial theorem kind of question. It depends on how it is phrased. So in this case, we have a lab testing. Okay, we know from lab testing, in other words, we have empirical data to support this. When a 1 is transmitted, there's a chance of 2% that it is erroneously received as 0, which basically means you have a 98% chance that it is received correctly. Okay, 2% chance erroneous, 98% correct. When a 0 is transmitted, there's a chance of 4% that it is received incorrectly as a 1, and 96% of a chance that it is received correctly. So suppose a 4-bit pattern 1001 is transmitted. Assume the transmission of a bit does not affect the error probability of any other bits. This part basically states that the probabilities are independent. Okay. One event or one trial does not affect the probability of the other trials. We want to analyze the overall error rate. In the following space, create a table so that each row represents a pattern, a data pattern that can be received. And how many rows are we talking about? How many ways can I receive 1, 0, 0, 1? Remember, a 1 can be received incorrectly as a 0 can be received incorrectly as a 1. So how many rows are we talking about?
8 times?
16.
16, okay, very good. Why 16?
The 4 to the power of 2.
Other way around.
2 to the power of 4.
They turn out to be the same, yes, but it is 2 to the power of 4, okay? So why is it 2 to the power of 4, and how do we work this out? So for this, I have to say, one of your classmates came to my office hour today, and we were just working on this, and I found a better way to explain this. So this is cool. So what we'll do is we're going to look at a picture, okay? And I think for this picture to work well, because we got 16 of these things, it might be better for me to look at it this way. Okay, so we have a 1 being transmitted. So a node is corresponding to what is transmitted, and an edge is or an arrow is corresponding to what is received. Okay, or the label of an arrow indicates what is received. Is that okay? So the first bit transmitted is a 1, and it can be received in 2 different ways, right? It can be received correctly as a 1, can be received incorrectly as a 0. Is that okay? 98% chance ending on the left-hand side, 2% chance of landing on the right-hand side. Is that okay? Now, at this point, I'm transmitting a 0. I'm transmitting a 0 on both sides of the branch because, remember, the nodes is dictating what is transmitted. And I'm transmitting 1, 0, 0, 1. What I'm trying to analyze are the chances of, okay, if I transmit 1, 0, 0, 1, what are the chances that I might receive it as 1, 0, 1, 0? That's what I'm trying to figure out. So this 0 can be received as a 0, can also be received as a 1. This 0 can be received as a 0, can also be received as a 1. So I'm using the standard of the left edge is the one that is correct, received correctly, and the right one is the one that is incorrect, it is received erroneously. Okay? Because it's better to explain the standard, so this way you know how to make your own graph. Okay? And then the third bit transmitted is also a 0, so we get 0, 0, 0, 0 here, because each level should have the same bit transmitted, 1, 0, 0, and then the last level would be another 1. Okay? So this 0 can be received correctly as a 0, can be received incorrectly as a 1, correctly as a 0, incorrectly as a 1, 0, 1, 0, and a 1. Is that okay so far? Okay. So the last bit transmitted is a 1, and remember the entire level has the same value because it is only representing what is transmitted. So once we have this branch, okay, you can see that this last one transmitted can be received correctly as a 1, can be received incorrectly as a 0. So I'm just repeating this many times. Okay, this is taking a little bit of time, but the video is being recorded, so if you don't have time to copy this, that's okay. But you might want to write down certain things that's actually happening in your mind, because I cannot, this is not a psychic projector or psychic projection screen. I cannot record your thoughts. Only you can record that. Okay? All right, so this is the entire tree. Okay? I transmit 4 bits, 1, 0, 0, 1, and there are 16 ways of receiving those bits transmitted. Okay, so I'll work out a few, okay, because working out this entire table is going to be super duper boring. Okay, but the first thing I want to do is to label each branch with its probabilities. 0.98, 0.96, 0.96, and then 0.98 here. Is that making any sense? Because the probabilities of a 0 received correctly and incorrectly is different from a 1 received correctly and incorrectly. Yep?
So for using error checking, could we just verify each level has a combined probability of 1?
Yes. Yep, exactly. So this is 0.02, this is 0.04, this is again 0.96, 0.04, 0.04, 0.96, 0.04, and I'm just going to work out, I'm not going to work out the entire table because that's just going to be a little bit boring. Okay, so 0.98, 0.02, and so on. So are we doing okay so far with the graph at this point, the tree? Okay, so now the question is, okay, can you enumerate and tell me what patterns can be received? Well, let's follow the branches. Okay, so I'm going to choose a blue, okay, this time. So 1 is received as a, so if I receive it as 1, 0, 0, 1, then what are the chances of receiving those 4 bits as 1, 0, 0, 1? Well, you follow the branches. There's a 98% chance that I would end up here. Of that 98%, 96% would go here. 4% would go here. Is that okay? So that means if I want to label the probability of this node here, that is 0.98 times 0.96. Is that making any sense? Is that explaining why we are multiplying? Because, and then the chances of landing here is going to be 0.98 times 0.96 squared, because the chances of landing at this point is 0.98 times 0.96. Of that probability, 96% chance we end up here. And that's why we multiply the 96% to whatever we have earlier. Which also means, the probability of all the way down here is going to be 0.98 squared times 0.96 squared. The 0.98 represents the first one and the last one received, and then the 0.96 squared represents the 2 middle bits received. Is that okay? And the pattern that we are receiving down here is 1, 0, 0, 1, which means everything is received correctly. Yep. Question? Okay, we'll pick another branch. We'll pick another leaf, okay, to analyze. We'll just pick this guy here, okay? Yeah, we'll pick this one. Okay, this is the next one we want to analyze. Okay, how did we get here? A 0.02 chance to get here, and then of the 0.02, we have 0.96 chance of landing here. So the probability of here is 0.02 times 0.96. Of this probability, of this particular probability, we have another yeah, this is correct. So of that probability, we have another 0.04 of a chance to end up here. So the probability of landing here is 0.02 times 0.96 times 0.04. It really is just the probability of each branch multiplied together. So now we have this last one here, okay? This last one is a one received correctly as a 1, which is 0.98. So the probability of landing here is 0.02 because of this branch times 0.96 because of this branch times 0.04 because of this branch times 0.98 because of the last branch here. But what are we receiving? What is the probability of? Is the probability of receiving a 0 because of this branch, a 0 because of this branch, a 1 because of this branch, and a 1 because of the last branch here. So I just want a table that shows me that you understand how to make this happen. Now, obviously, writing down all the 0.98 or the 0.06, 96 and stuff like that is time-consuming, and that's why I suggested to use variables. Just use P, Q, R, S, or something like that to make it easy so that you can write it easily. Yep.
What was the question again? So what were you specifically solving for?
Okay, so the question is, suppose, so assume the transmission of a bit, in the following space, create a table so that each row represents a data pattern that can be received. So that table is going to be depending on how you organize, okay? Because if you organize like the tree that I have, it's not going to be like a sequential binary numbers. But if you organize as sequential binary numbers, you just have to kind of work out the P's and Q's differently. Okay. On each row, use a formula to express the probability of that data pattern being received. So that would basically correspond to this value, and so on. Yep.
If we just let every percent equal to a variable, can we just leave it as a variable in here?
Yep.
Yeah.
Yep.
So like principal product of variables.
Yeah, just for notational simplicity, yes,
Yeah.
absolutely. Use variables whenever it makes sense. And I just noticed that my microphone is in my bag. It's still recording. It's just, I don't think it's going to be muffled. It's just different. It's okay. I saw the signal bar and it was still good. There's no need to work out the exact numerical values, and you can use variables in some equations. Okay, and you can refer to the same formula on multiple rows. So in other words, there are only so many values you need to work with. So if you find out, oh, half of these things have exactly this component, give a variable name to it so that you don't have to write that common part out. Is that okay? Sure. Yeah.
So
go ahead.
what you did wasn't enough. We would have to make the formula to represent how that process works, like an
Yes.
algorithm.
Now, for some of you can say, okay, but I can programmatically express how this table is generated. Okay. In the actual exam, if you say, okay, this is really tedious, but I can write the code to generate this table, you can come and ask me, can I just give you the C code to generate this table instead of wasting my time to write out each entry? And if I say yes, you can go ahead and do it. Okay, but you want to ask me first before you say, okay, this is the alternative way of answering the question. Is that okay so far? Okay. So that's from Spring 16. There were a few questions very similar to this one in the other two exams. So if you look at the fall exam, I think it has a question that we might have talked about already, but I'm not sure, so we'll take a look first.
You're asking for a generic formula for...
Yeah, I'm a little confused.
Nope, not generic.
You just want the individual formulas for each bit pattern?
Yeah.
Okay.
On each row, you specify what pattern,
Okay.
and then you specify its probability.
Right.
Yep. And there should be 16 rows. Yep.
Wait, so you're talking about like the when you said like 0.98 times 0.96 for each part? That's the formula you're referring to, or?
Yeah.
I'm still
But you can make it
confused on
easier by using variables. So if I were to do it like this, okay, this is not in a table format, obviously, but I'm using this to explain, how you come up with the numbers. So each row should have to indicate what pattern is being received, and also, some kind of formula to tell me what is the probability of receiving that particular bit pattern. So this will be one row. This is another row. This is another row where this is the pattern being received, and this is the probability of receiving that pattern. So you just have to work out the other 14 items. Yep. Mm-hmm.
That's just the answer, but we have to still write out the
Yeah.
16 items?
Yep. As I said, you can also come up with a general equation to do it if you figure out, hey, I can express the same logic, but using either an equation on each row, or you can use an algorithm to do it.
There's like a much smaller way to draw it out and easier. Have it here. Do you want to share it with everybody?
Sure. Well, since we have the document camera, if you want to bring it up, that's fine. Yep.
I'm still a little confused on the far left when you have the 0.98 times the 0.96, with both of them being squared. How does that result in the 1001?
No.
Just write it down like that.
Uh-huh.
Just pick your numbers accordingly. And
These are just
Okay.
initial next to it?
probabilities is pretty much the same as yours.
Okay. But it's not expressing, how you pick from each row.
Like if for this one I say 0011, we're just
Uh-huh.
just pick point
I just
2,
put initial next.
0.96,
So you would need to
0.04.
include more
I'm assuming he doesn't
instruction
definitely
to
wants
follow this table, to follow this format.
Okay.
Yep.
All right.
Okay.
Mhm.
You just want us to initial next to our previous signatures on that?
Yeah.
Okay.
Yep. Just initial would be fine. Okay. But thank you for sharing. Yep. So are we still doing okay so far with this?
Yeah. Still
Okay.
a little confused, but
So still a little confused?
on the how that results in the 1001, is that just that it has the highest probability on that side, or?
Okay, how about this? You can also express it like this, okay? So you can say for each row, okay, the pattern is, okay, so you say A, B, C, D, okay? So you basically say, okay, in general, I can receive, the 4 bits as 4, received bits, A, B, C, and D. And then the probability is going to be, if A is a 1, okay, then the probability of that portion is going to be 0.98, okay? Otherwise, the probability is 0.02. That accounts for A, okay? Times the probability related to B, the bit B. B is a 0 if it is received correctly. And if it is received correctly, it's 0.96. If it is received incorrectly, it's 0.04 times C. C is kind of like B because it is supposed to be a 0. So we're looking at 0.96 versus 0.04 again. And then the last bit D is supposed to be a 1. So if D is a 1, then it is 0.98. Otherwise, it is 0.02. So you can say there are 16 rows on the table. There are 16 rows in this particular table. A can be 0, 1, B can be, so I have to make it clear. There are 16 rows in the table. And then for each row, okay, A can be a 0 or 1, B can be a 0 or 1, C can be 0 or 1, D can be 0 or 1. But to make it absolutely clear, okay, I would just spend the time and write this pattern. It doesn't take long. Okay, thank you.
Could we just say the probability equals the percent times the number of true ones, true zeros?
Nope, no,
ones
that.
plus zeros.
But you're not. But then you need to enumerate. You need to tell me how many rows we're dealing with.
How many rows?
Yeah, there are 16 rows. So that doesn't show me that you have 16 rows.
There are 16. What do you mean 16 rows?
Because the question asks you to make a table, right?
Okay, so I would have to use this formula on each of them.
Well, you can combine that with this table. Okay, so A, B, C, D, and then this is the equation. Call this X. Is that okay? Yep.
Could you give us a 3-digit binary number of the test?
Well, there's one test with only a 3-digit number. Okay. Okay, so let's take a look at the other one. Okay, so I think I got to open it down here. Nope, this is the one that we just looked at. Okay, this is the other one. Oh, this one is really fun too. Different way of asking pretty much the same kind of question. All right. So this one, is telling you that this one is telling you the observation, but we don't know the probabilities. Okay. So when you analyze this one, it's kind of the same thing, but it's a little bit different. So this one says, it is observed. Okay. I know for sure that I'm transmitting 1, 1, 0. Okay. But when I transmit 110, the chances of receiving 110 as 110 is 0.576. In other words, I transmit 110 1,000 times, and then of the 1,000 times, 578 times it is received correctly as 110. And I observe that if I transmit 110 1,000 times, the chances or the number of times it is received as 101 is only 16 times, and so on. Is that okay? So we are observing the probability. We don't know for sure in theory what it is, but I'm just telling you the frequencies of the observations. Is that part okay? So now the question is, how do I find out the exact value? So in this question, the question is saying use P, the variable P, as the chance of transmitting a 1 and receiving as a 0, and Q as the chance of transmitting 0 received as a 1. Okay, so these are the incorrect probabilities. Okay, express the chances of receiving a transmitted 110 as 110, 101, 011, and 010 respectively. So I want to use the P's and the Q's to explain why we have 0.576 and the other numbers. Yes?
So a correctly transmitted would be 1 minus P, right? Or 1 minus
Yep.
Q. So you just multiply those based on...
Yep. Yep, exactly. Okay, and then I want you to express how to resolve the terms P and Q. In other words, how do we find out exactly what is P and what is Q? Because I want to know what are the chances of receiving incorrectly as a 1, 1 received incorrectly as a 0, or 0 received incorrectly as a 1. So how do we solve that problem? That's what it's asking. Okay, so can we flip to the documents camera so I can solve the question in just using handwriting? Okay, because I think this is going to be helpful. This is the first time that I use a chart or a tree to explain this, because I think this is going to be helpful. Okay, so in this case, what we are transmitting is 1, 1, 0. I'm putting this on the side just to remind myself what each level is transmitting. Okay, then we can draw the tree exactly the same way as before. Okay, a 1 transmitted as a, a 1 transmitted can be received in 2 ways. It can be received correctly as a 1, can be received incorrectly as a 0. Whoops, I labeled the branches incorrectly. Remember the arrows or the label on the branch itself indicates what is received. The nodes are corresponding to what is transmitted. Is that okay? So now we have this 1 transmitted can be received as a 1, can be received incorrectly as a 0. This one can be received correctly as a 1, received incorrectly as a 0. And now we transmit the 0. See, you guys asked for it. You're only having 3 bits. You got 3 bits. Okay, this 0 can be received correctly as a 0, can be received incorrectly as a 1, received correctly as a 0, incorrectly as a 1, correctly as a 0, incorrectly as a 1, correctly as a 0, incorrectly as a 1. Now, but this question is even more friendly than only having 3 bits, because of the 8 possible branches, only 4 you have to analyze. Okay, I specifically asked for the analysis of only 4 of them. Okay, so getting back to the question, the 4 that I want you to analyze is 1, 1, 0, which is everything is received correctly. So the 1, 1, 0, you have to read the edges. 1, 1, 0 is this guy. Okay, cool. So we know that we have to analyze this one. I'm just marking all the ones that we have to analyze. The next one is 1, 0, 1. So you have 1, 0, 1. So that would be this guy. The next one is 0, 1, 1. So we have 0, 1, 1, which is this one here. And then the last one is 0, 1, 0. So we have 0, 1, 0, which is this one. So those are the only 4 branches that we have to analyze for this particular question, not even all 8 of them. Is that okay? So far so good? Okay. So the way we label the branches is P is the chances of a 1 received incorrectly. So that means the chances of landing here. I'm going to use blue to represent the probability. So this is P, and this is going to be 1 minus P. Yeah, P is the chances of receiving incorrectly. Okay. So this one is 1 received as a 1, so it is also correctly. So this is 1 minus P squared, because this branch has a probability of 1 minus P. Of that probability of 1 minus P, this branch is also 1 minus P, so that's why the chances of landing here is 1 minus P squared. The probability of this branch is 1 minus Q, so that means at this point we have 1 minus P squared times 1 minus Q. That's the probability of landing here. Is that okay? And we can work out the other 2. Okay, so we have 1 minus P, this is P itself, and then this is also incorrect, which is Q. So we have this one, we have 1 minus P times Q. Because a 0 transmitted but a 1 received has a probability of Q. That's part of the question.
So 1 minus P is the probability of it being correct?
Of a 1 received correctly.
As correctly.
Yes.
And 1 minus Q is the probability
of a 0 received correctly as a 0.
Okay.
Yep. Okay. So we'll work out all 4 of them. So we got P. This is 1 minus P times P. So this is going to be 1 minus P times 1 minus Q, because it is a 0 transmitted but received correctly as a 0. This is the last one. So with this one we have, it's just different only by 1. So instead of 1 minus Q, we just got Q. So it's 1 minus P times Q. That's it. Is that okay? Okay, so we want to label what bit pattern is being received. So this one is received as 110, which is everything is correct. This one is 101. This one here is 0, 1, 0. and this one is 0, 1, 1. Okay? So now we go back to the original question. I'm just going to copy down the probabilities, the actual numbers. So the numbers are 0.576, 0.016, 0.016, and 0.144. Going back here. Okay. So now, okay, excuse my 0.576 because I wrote down the incorrectly, and I still haven't bought my whiteout yet. So maybe I'll just use a little tape thing. Okay, so now the question is, how do I figure out what is P and what is Q? What is the easiest way to do this? Absolute easiest way to do this. You look for two that are very close, and then you say, let's divide those, right? So of these, there are a few options. I think there are a few options to do this. Okay, so you can see that these two are pretty close, right? They're only off by 1. Let's see. These two are also pretty close. They're only off by the first one. So you can pick either one, okay? Okay, I'll pick these two, just because they're right next to each other. So now we have 1 minus P times 1 minus Q divided by 1 minus P times Q being 0.16 divided by 0.144. Is that making any sense? So you cancel out the terms like that. So now you have 1 minus Q divided by Q equal to 0.016 divided by 0.144. And I trust that you guys can take this one to the end. Yep.
For the one on the far right, and then the one second to the right, or third to the right, they have all the same variables. How would that work out?
That would not work out if you. Oh, okay. So my equations are wrong. Like that. You mean these two?
Yeah.
Probably made a mistake somewhere. Incorrect. PQ. And then it's got 2 incorrect, which is also PQ. So I got the chances incorrect. Yeah. I think the numbers are supposed to be reversed. This one is supposed to be 144. That one's supposed to be 0.016.
Okay.
Yep. Yep. So we have to exchange these values. This one is 0.144, and this one is 0.1016. So that means these ratios will be opposite. But that's basically the idea, So now you can solve for Q. Once you solve for Q, your P is easy.
Well, we have Q.
Huh?
We have Q.
Ratio flips.
This ratio is going to solve for Q first, right? So once you know what Q is, you can plug in Q to one of these equations and solve for P. And let me just go back to the question and see how far you have to take it. Then express how to resolve the terms P and Q. There's no need to actually find the terms, so you must express P or Q in a way that is directly resolvable, which means P has to be on one side of the equation, and then the rest, the constants, have to go to the right-hand side. That's it. Is that okay? So in this case, if I were to take this, okay, remember I got the numbers incorrectly. Okay, so I'm going to continue over here just because I ran out of room here. So now we can say 0.1016 times 1 minus Q is 0.144 Q. So when you multiply this whole thing out, then you can say 0.016 of this one is the same thing as 0.144 plus 0.016 of Q. So Q is, ooh, that doesn't look right to me. Yep.
That one transmitted as a 1 was P.
Hmm?
Is that right? One transmitted as 1 is P.
1 transmitted as 1 is 1 minus P. This doesn't work out right. Because this number is going to be, oh no, this is okay. So it's 0.016 divided by 0.144 plus 0.1016, and leaving it like this is sufficient. So you don't really need a scientific calculator to do it. And then the rest of the instruction is to plug this into one of the equations with P, and then you have then you can solve with the probability of P. Yep.
So, different question. Like in a coin toss, we multiply the probability kind of with a combination, but
Right.
here we're not doing it because it's independent of each other. That's why.
Yes. Okay, that's a very good question. The question is, when do we use the binomial theorem, which uses combination, and when do we use this, which is not using binomial theorem? So with this one, we are not using binomial theorem because the ordering is important. Okay, you can see that this one is 110, 101, 010, 011. So we are not counting the error bits regardless of the position. We know exactly where the error bits are at certain positions of the received bit pattern. So that is when we do not use combinations, because we are not considering ordering insignificant. With the other one, when you're doing coin toss, in a casino, they just count the number of heads and the number of tails, regardless of where the position of each trial. So that's why we're using combination in that one. Yep.
And that's the difference between permutation and combination, or is that not related?
It's also different. Okay. In this case, there's no permutation in this one either, because permutation means it is without replacement. In other words, once you use a particular outcome in a trial, you cannot have that outcome again in later trials. But in this case, if you received a 1 incorrectly as a 0, we can do the same thing again. So it is with replacement. The reason why, in a coin toss, it is a combination, it doesn't seem to make sense, right? Because if a coin lands on the head the first time, it can also land on the head the second time. So it seems like, hey, this is also with replacement, so why are we dealing with it as a combination? It is because of the way we encode that information. Okay, so let me explain that. It's on a different sheet here. So we are looking at head, tail, 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 but we are also saying that this is the same thing as in the casino, it is the same thing as this, equivalent to this, which is also equivalent to this, which is also equivalent to this. So there are 4 ways that I can have one head and 3 tails. That makes sense, right? So how come we ended up using combination? It's because of the way we code this. Okay, so the way we code this is we just use a set to indicate what is the position of the head. The first one. What is the position of the head? 2. What is the position of the head? 3. And this is 4. But what are the possible choices that the head can be at? We are choosing one out of the set of 1, 2, 3, 4. That's why we are using choosing, which is combination. Okay? Now, let's look at these cases where we have 2 heads and 2 tails. Okay? So if you think about 2 heads and 2 tails, the question now is, how many ways can I organize these coin tosses so that we end up with exactly 2 heads and 2 tails? Well, you can enumerate it using this way. So you can say, oh, we can have head, head, tail, tail, head, tail, head, tail, head, tail, tail, head, head, head. Oh, okay, I think I have exhausted everything here. So we now can use tail, head, head, tail, tail, head, tail, head, and there's one more, which is tail, tail, head, head. So they're exactly 6. Okay, so you go, okay, we can do it this way. But we can also look at it as, oh, we have 4 numbers to choose from, 4 ways that we can have a head. Choose 2 out of these 4. So that's combination. So that's why it is using combination.
So what we're asking, because we're asking how many heads and how many tails are going to be in the set, then we use combination. So if we want to do the same thing for a binary number, we ask, okay, how many 1s? If we had 2 1s and 1 0, what's the chances of that?
Yep. Okay, so this is another question. It is not in the test, okay, but I think it's a good example and it has direct applications. How many people lived through the era of modems? Okay, so with modems, when you set it up, you can set up 8 data bits, no parity, and 1 stop bit. Okay, 8 and 1 is the typical setup for a modern modem. But you can also set it up to have parity bits. So a parity bit is really just saying, okay, of the transmission of these data bits, what is the number of what is the number of 1s or 0s? I cannot remember which one, but there's a parity bit as a checksum of all those bits. Okay. I cannot remember. So you can look it up. You can say look up parity bit. Okay, so a bit that acts as a checksum calculated in such a way that the number of 1s in the set plus the parity bit should always be even. Okay, so let me just highlight which portion here. So the usual way is to set it up as even parity, and that's why you have 7-1-E. The E stands for even parity, and odd parity is really odd. No pun intended. It's unusual. Okay. So that means, okay, so using this particular definition, so when you transmit, let's say 0, 1, 1, 0, 0, 1, 1, 1, what is the parity bit of these 8 bits? Yep, the parity bit is going to be a 1 because when you add up all the 1s, including the parity bit, it should be an even number. Is that okay? So this is how people used to transmit. They used to do parity bit check, so that when you transmit a byte or when you transmit the small whatever quantity of bits, the modem can detect this by hardware. The receiving modem can say, hey, I'm supposed to get always even number of 1s, and somehow I got odd number of 1s, and I'm going to tell the transmitting modem and go like, we have a problem. Okay, there's a parity problem here. It actually doesn't do that, but it tells the operating system on the receiving side that we have a parity issue, and then whatever transmitting protocol you're using probably has a way to do the handshake and tell the other side, like, okay, stop, the last packet was received incorrectly, please retransmit, or something along that line. Does that make any sense? But parity bit is not really that useful, because when you have 2 error bits, then the parity bit, when you transmit 2 bits erroneously, they cancel out each other. Yep.
Or any even number of those bits.
Exactly. Any even number of bits transmitted incorrectly cannot be caught.
So it's only affects 50% of the time.
Yep. Okay. So let's look at this scenario here. So we're basically saying 8 bits transmitted. Okay, 8 data bits, not counting the parity. Transmitted. Okay. So I can ask, what are the chances? Okay, I should say 9 because 8 data bits. Okay, 8 data bits transmitted plus 1 parity bit. Okay, what are the chances that 2, 4, 6, or 8 bits are received incorrectly? Because this probability tells me about the probability of having an actual transmission error but not caught by the parity bit. Yep.
Should we also figure out whether the parity bit can be transmitted wrong?
No, that's why it's included here. So you have 9 bits actually transmitted.
Okay.
But of the 9 bits transmitted, if one of the data bit is incorrect and the parity bit is also incorrect, it won't catch it. So any 2 bits out of the 9 is fine. Oh, did I just say, any 2 of 9? 9 choose 2. Okay? So in this case, you basically, but this time you have to assume the probability is symmetric, which means a 0 transmitted received as a 1 versus a 1 transmitted but received as a 0 are the same. Okay? So now we say, okay, P is the probability of a bit received correctly. Okay, so this time I'm defining P a little bit differently. P is close to 1. It is the chances of a bit received correctly. So how do I figure out this probability here? The chances that we have 2, 4, 6, or 8 bits of 9 bits received incorrectly, meaning the rest are received correctly. So how do you solve this problem? Which theorem do we use?
Binomial theorem.
Binomial theorem. Very good. Okay, so we got 9 choose 2, right? 9 bits transmitted. Of those 2 are received incorrectly. So in this case, P is to the power of 7, Q is to the power of 2. Oh, well, okay, let's define Q. Q is 1 minus P. There we go.
Should it be P to the power of 2 and Q to the power of 7?
No, because P is the probability of a bit received correctly. 9 choose 2 is 9 of 9 bits, 2 are received incorrectly. So we have 7 bits received correctly.
I'm just going off of the formula you gave us, the M over N. M
What?
choose N, P to the N, and Q to the N minus N.
I think you switched to the formula.
You can, but it's the essence that is important. I can just choose. I can change this 2 to a 7, and it doesn't change the number, right? 9 choose 2 versus 9 choose 7 are the same.
Because you assume P and Q are the same, so it doesn't matter if it's the 7 or 2.
No, P and Q are not the same. They are very skewed. You don't want P and Q about the same. I'm not going to buy that modem.
But you assume that transmitting one or receiving it correctly or incorrectly are the same.
Yes, the chances of a 1 received incorrectly as a 0 and the chances of a 0 received incorrectly as a 1 are exactly the same. But the P and the Q's have nothing to do with what is transmitted. It is P is just a bit received correctly. A 1 received as 1, a 0 received as a 0. Yep.
You get a mark as like T and F. Like,
What?
would it be easier to mark those like T and F and then true false? So it's kind of like self-documented.
Oh.
I don't know.
Well, you can define the variables any way you want. I mean that's that's the whole point. Is I just need to know what the variables mean in this context. Okay, so is that okay? I mean 9 choose 7, and we're choosing the number of bits received correctly. Yep.
Are bits normally received with similar probabilities? Like when 0, like the error rate would be roughly the same?
It depends on why it is not received correctly. If it is because of a bias of the line, it's floating, there's a certain tendency to float in one direction, then they would not be symmetric. But if it is because of electrical noise that is interfering with the modulation and the demodulation process, then they would be about the same. Yep.
Don't you then need to do it for 9 choose 5 and 9 choose 3?
Oh yeah, oh yeah. We have to add those two.
Okay,
Yep.
So that first one is just the chances that 2 bits were received incorrectly.
Yep.
And then the next one is 4.
There's also 9 choose 1. So we have P3, Q6, and then this time we have P1, Q7, Q8 actually. So this number here, this would be the answer. X would be the answer. Because it is the total chances of uncatchable error transmissions or transmission errors that cannot be caught by a single parity bit, which is obviously of real, actual concern because when you're using a modem, you need to know what are the chances that the parity bit cannot catch a particular error. Is that okay so far? But you can see how this one, even though it is a question about transmission error, but I'm using the binomial theorem to analyze it. Because it doesn't matter which 2 bits we're talking about. Are we talking about bit 0 and bit 1 versus bit 0 and bit 2? It doesn't matter, okay? It can be one of the data bits and the parity bit itself. I don't care. Any 2 bits out of the 9 bits transmitted, if those 2 bits are received incorrectly and the other 7 bits are received correctly, I cannot catch that transmission error using a single parity bit. And that's what I want to analyze. So are we doing okay so far with the analysis of this one? This is not in one of the exams, which means I just used up a possible question in your exam, because I'm talking about it now. But I can always reverse the question and say, okay, we can observe, okay, that there's a certain chance of receiving a byte, everything checks out, the parity bit checks out, but it's actually incorrect, okay? Go back and figure out what is the probability of a bit received incorrectly. Yep?
Can you explain again when we use binomial theorem and when we wouldn't?
The binomial theorem is used when you are when positioning is not important. In this case, it doesn't matter, of the 8 bits, of the 9 bits actually transmitted, it doesn't matter which 2 are the issues, right? In other words, okay, this is where right, this is why we use binomial theorem, because this bit may be off, this bit may be off. Okay? But it can also be this bit versus this bit. Okay? But it can also be this bit versus this bit here. So when positioning does not matter, I'm just counting how many out of how many else, then binomial theorem applies, which is the same thing as a coin toss. I don't really care whether it's the first 2 tosses that end up on the head. I just need 2 heads and the rest are tails. So that's basically why we are applying the binomial theorem in this case. That's a very good question. Whereas the other ones, when we analyze the other error bits, they are not binomial theorem type of questions, because I specifically say that this pattern is transmitted, but this pattern is received. That one bit is received correctly, the second bit is received incorrectly, the third bit is received correctly, the fourth bit is received correctly. So ordering is important in that case. Now when ordering is important and it is with replacement, you're almost guaranteed that binomial theorem is not going to apply. Yep.
What if you asked how many of the combinations have the same probability?
How many of the combinations of this have the same probabilities? That would be combination again. That would be binomial theorem again. But that is only applicable if the error chances are the same. 0 received as a 1, 1 received as a 0. Only if those are symmetric. Because if they are not symmetric, then you are not going to be, it's not this or the other one. You have 4 cases to deal with in that case.
When you say symmetric, you mean that one is 0.5 and the other one is 0.5?
No, symmetric means a 1 received as a 0 has the same chance as a 0 received as a 1. So the error rates are the same. Because there are 2 ways to err, right? Yeah, go ahead. There are 2 ways to err. You can transmit a 1 and receive it as a 0. You can transmit a 0 and receive it as a 1. Now physics, depending on the actual mechanism, those chances may not be the same. But if they are the same, and I'm interested in counting number of error bits, then the binomial theorem applies. Is that okay? All right. Yep, go ahead.
And so the test, we're not doing any of the sci-fi stuff?
Oh, yeah, we are.
We are?
Yep. Okay. So we are moving on to Okay, so this one is proof by induction. So we are going to have some proof by induction and some proof by contradiction. Okay. So let's go back and talk about proof by contradiction and proof by induction. Okay. So how much do you remember those discussions? Nothing. Okay. Very good.
I just remember I think it wasn't proof by induction. It resulted in 1 or whatever.
Say again?
When you showed the proof for it wasn't induction, the one where it resulted in 1 and 0 is when it's proof by contradiction. But.
Okay. So let's go back to something that you're familiar with or should be familiar with. Okay. I hope you guys still remember this. Choose a different color. I goes from 0 to n, and we're just summing I itself. Okay, so quick review. Do we still remember this one? This one really should be in your mind now. Okay, it is what? It's n times Is it n plus 1? Okay, divided by 2. We can always check, right? Okay, let's add up to 5. Okay, 1 plus 2 plus 3 plus 4 plus 5 is 6 plus 6 plus 3. 6, 3 is 15. So is that 5 times 6 divided by 2? Yep. Okay, that checks out. Okay. So this time I want to prove this by induction. Okay, we didn't prove it by induction before, but this time we can do it by induction. So what are the 2 steps of proof by induction? We need a base case, right? So the base case is basically to say, let's fix n to a specific value and prove that for that one single value, the theorem holds true. So we say, well, let's consider the case when n equals to 0. Okay, all right. So if n equals to 0, then the summation of I equals to 0 to 0, I is going to be just 0. Is that okay? 0 equals to 0 is okay, right? But this 0 can be 0 times 1, the whole thing divided by 2. Right? You evaluate the left-hand side when n equals to 0, that whole thing is 0. You evaluate the right-hand side when n equals to 0, that is 0 as well. So we have 0 equals to 0, so the base case is now proven when n equals to 0. Is that okay? So now you say, okay, what is the induction step? Okay, this is the induction step. The induction step says, in general, it says, assume the theorem is true when n equals k. Prove that the theorem will also be true for when n equals to k plus 1. Okay, so we'll say, assume the theorem is true for n equals to k. Prove that the theorem is true for n equals to k plus 1. What theorem are we talking about? Can be this one, can be something else. Okay, in other words, this can apply to a lot of different theorems. But in this case, the theorem, this is our theorem. All right. So now we say, okay, fine. We'll look at the case when summation of I equals to 0 to n to k plus 1 this time. In other words, this is n being k plus 1. Is that okay? How can we rewrite this one? How about we break out the k plus 1, and then the rest is just I equals to 0, summing up to k, I. Would that be okay? I just broke out the last term. Okay? But the idea of breaking up the last term is so that we have this thing here. Hey, that is cool because the assumption says the theorem is true for n equals to k. This is the case when n equals to k. So now we can say, oh, okay, this whole thing is just k plus 1 plus apply the theorem, which is k times k plus 1, the whole thing divided by 2. This is the most important part of proof by induction. The rest is algebra. Is that part okay? The induction step states that you assume the theorem is true for n equals to k. But then we have to use that assumption to prove that the theorem is also true when n equals to k plus 1. Okay, so we are making use of the assumption here, which is the most important step of proof by induction. So the rest is really just saying, okay, let's make everything divide by 2. So we have 2k plus 1 plus 2, and then plus we have k squared plus k, right? So it's just a matter of reorganizing the whole thing so that we end up with k plus 1 times k plus 1 plus 1. Or k plus 1 plus 2. Okay? The quickest way to do it, okay, so let me bring this to this side here. Okay. So we have 2k plus 1 plus k times k plus 1. Okay, the whole thing divided by 2, right? So the best, easiest way to do it is to factor out the k plus 1, so we end up with 2 plus k times k plus 1 divided by 2, which now can be rewritten as k plus 1 times k plus 1, the whole thing plus 1 divided by 2, and that's the end of the theorem. Is that making any sense?
Yeah.
Okay.
I don't know why you decided that you would do the when you expanded right there. It seemed like an extra step.
Yeah, it is an extra step. I could have just gone here. Yeah, it should have gone here to here and not here. But the most important part, the other parts are all just algebra. From this step to this step here, okay, is how I made use of the induction assumption. That is the most important part. So in the exam, what you need to do is to tell me what is the base case. The base case typically is really easy to prove because it's one extreme of the range where the theorem applies. Okay, just pick one end, usually when n equals to 0 or 1. Okay, the induction step is the kind of the tricky one. So you have to tell me, assume the theorem is true when n equals to k. Okay, because some people choose k minus 1. Okay, if you choose n equals to k minus 1 as your assumption, then you have to prove n equals to k when the theorem still applies. Okay, in other words, between the assumption and what you're proving can only be off by 1. If you assume n equals to, if you assume the theorem is true when n equals to k minus 1, prove the theorem is true when n equals to k. If you assume the theorem is true when equals k, you can also go backwards. Okay, you can say, oh, then I can prove the theorem is true when n equals to k minus 1. You can go in the opposite direction too. Okay, sometimes it makes sense to go in the opposite direction because when n can go positive and negative, in other words, when n can be any integer, then where do you start? There's no end in either side, right? On both sides, you can go infinite. So start with 0, but then you have to break your proof into 2 parts. One part uses induction in the forward direction. The other part uses induction in the negative direction. But they work the same way, in the same sense. Is that okay? All right. So is this one okay? Proof by induction?
So you're saying when it can go negative, you have to prove both directions?
Right. So when you have, when it goes in both directions, then you have 2 induction steps to prove. You still only have one base case, but you'll have 2 induction. Yep.
Will you be posting a key for these practice interhams?
We're kind of talking about it.
Well, just a couple questions though. There's
Yes.
quite a lot of questions on those.
Okay. I will try to get to it. Yep. Go ahead.
Shouldn't your final step for the proof you just did show that your answer is equal to what we were wanted, which was
Yeah, so it's going from here. So the equality chain goes from here
all the way down.
all the way down to here.
And then should you show that that's n times n plus 1 over 2? Or do you have to?
But this is already the proof that the theorem is true for n equals to k plus 1. Because you put, this is n, and this part is n2. Yeah. So this is already sufficient. All right. So this one is using proof by induction to prove that the theorem, this is the theorem. The theorem says, x is an integer, okay, z star is integer. So this one says, for any x, f of x equals to x squared. F of x is defined to be, recursively. Nope, I take it back, sorry. So x is defined to be like this. It's defined recursively. So I want to prove that in general, f of x is just x squared. So how would you do this?
Use a base case.
Okay, the base case, what would you use as your base case? It's a recursive definition.
0 is not positive, so you have to start with 1.
No. The base case is when f of 0 is 0 is your base case. Because that's your end of the recursion.
0 is not. 0 is not positive.
This z star means any it means any integer.
We said we're C plus.
Represents all the non-negative. Okay, fine, we'll do non-negative. But this also applies to negative integers too. But okay, let's do this with all the non-negative integers, which means starting with 0. So your base case is still going to be this one. This is your base case.
Okay.
So if this is your base case, then you say the theorem, which is this one here, is true for x equals to some k. Then you have to prove it is also true for k plus 1. So what you do in this case is you apply here. Now this one is really easy in a way because the way f is defined is recursive already, which means it is very easy to make use of your induction step assumption. Okay, we are running out of time today. I cannot continue to talk about this. So we'll continue with this one on Wednesday. Okay, but there are proof by induction examples in I think all 3 tests. So you might want to kind of work on those as much as you can. Yep, go ahead.
Isn't the test on this?
Well, I'm going to postpone the test. But you can see how this is kind of important. So you guys need to read the practice test, both proof by contradiction and proof by induction, because that's what we're going to talk about on Wednesday. Yep.
Dumb question, but what notes did they have the proof by induction in again? I was trying to remember which one it was. I was
Proof
reading.
by induction is in.
So I was looking. I thought it was in propositional logic, but maybe I'm off by one.
Binomial theorem.
Binomial theorem?
Yeah, binomial theorem is where it is first introduced.
Okay.
Yep. But the basic idea is still the same.
Yeah.
When you have a base case, you have an induction step.
Yes.
And the most important part of the induction step is you have to make sure that